Hi there. Here are some instructions on how to do Fourier transforms and peak fitting on Fourier transforms in the frequency domain using Origin 2022. So first off, we got a file just downloaded that has some pipe organ recorded in as a WAV file. And I'm going to go ahead and open that, and then we'll switch over screens. File open. All right, so let's see. First off, there's my puppy. I love my puppy. My puppy's about 6 months old, and here is some pipe recording. So to do a Fourier transform and then fit some data, we first all have to plot one of these sets of data, and then we can cut off the edges of the data and only do the Fourier transform on the middle. So to do that, I'm going to click down here without having anything selected up top. And then this little menu right here pops up. I'm going to choose, oh, one more thing before we do that. Notice right here how it, WAV file saves it as an index and then also tells you what the dx is. And so first we have to change column A to be the dx time length interval. And so I'm going to right click over here and I'm going to view and I'm going to do FX. It said it was viewed available to be seen before, but no, it wasn't really. So now I'm going to do is equal to square bracket I, which means index over here, minus 1 square bracket, times it by, and I'm going to times it by this number, 2.0833 e to the 5. 2.0833 e to the negative 5. And what that's going to do is going to change this whole column to x in time steps. And so these units now are in seconds. This right here is just simply an amplitude of a voltage. It's a signal reported by a cell phone. All right, so now that we've established those levels, now we can click on this bar down here, and we're going to choose column A, which is going to be, I should change that, time, and then column B is going to be our Y. I'm going to go ahead and click OK. Now that creates a graph of this, and right now speed mode is on, and so I can turn off speed mode. There's a lot of points of data in here. And now what I'm going to do is I'm going to select the region of interest by just moving over to there, and then I'm going to move this one over to there, just right inside the little edges where they start. And I'm going to do analysis, signal processing, FFT. And right here it shows what the range is. It's 105,162 to 284,131. And now I got some other options. I can do output, and I just want the regular base settings for most of this stuff. And I could get the amplitude and phase. My plot, the only one I'm really concerned about right now is the magnitude. With some more advanced stuff, we can look at some of these other components like the real and imaginary. But at the moment, we're only worried about the magnitude. That's the complex conjugate of the real numbers multiplied by, well, sorry, it's the complex conjugate where you change the sign and now you can get a real magnitude out of the real and imaginary squared added together. That's a complex conjugate. I'm going to go ahead and hit OK. Now when I do that, it created a graph, or it created a set of data, and that set of data is going to be right here. And it does create a graph, but I want you to actually create a new graph. And so this is the frequency. And if you notice, we have a resolution of about 1/4 of a hertz, and that's as good as resolution as I can have. Now I can select these two columns, and I can plot a line. And what it shows me is two peaks and then a really flat line. So I can zoom in by using the magnify tool. And if I was to zoom in down here to see if there was any other peaks, there's a little bit, but for the most part, there's only one harmonic off this main peak. And so I'm going to zoom back out for a second, and then I'm just going to zoom in on this first peak right here. And it's not a perfect peak. Notice how there's some messiness to it. And next, to fit a Gaussian peak to this, I'm going to once again select the data, drag it in a little bit, drag it in a little bit, and notice how it's clipped right there. There was too much power, so this FFT was actually clipped. So now I'm going to go ahead and do analysis, fitting, nonlinear curve fit, open dialog. And I'm going to choose peak. Let's see, where are my peak functions? It might be under spectroscopy as well. Let me just double check. Nope. Oh, there we go, Gauss App. All right, parameters. Now it kind of chose its own parameters, and notice how it is actually a pretty good fit. So I'm going to go ahead and hit fit, and it might not have a great standard deviation and everything, but at the same time, these square pipe organs aren't perfect. They're not perfect. And so there's the peaks to this fit right there. Or there's the, what am I trying to say? There are the parameters of this fit. The first one, this y naught is the amplitude. And that's not that important. We could calculate what the amplitude is with a number of parameters, and that's where I'd have to dig up an old lesson to do that. But so that's not that important. That's just simply the height of the peak. The next one is important, XC, and that's the frequency. Notice how this says frequency 120, and this frequency right here is 115.9 and some change, and then it has plus and minus 0.02273. Now the width is also can be known as the Q factor. The narrower the signal, the sharper or the easier it is to get a single frequency, a single tone, or a single note. Now, if the Q is really wide, then it covers over a range of notes, and it's hard to tell which one you're playing. And so this is a fairly narrow Q, it says, or a fairly narrow width, and it says 0.29, so a quarter of a hertz, well, a third of a hertz. And then finally this A right here, let me just double check the formula again. Oh, sorry, the Y naught and then the A. Oh, sorry, Y naught is how shifted it up, and then the A is the amplitude. And so there's our first peak fit. Let's go ahead and zoom back out, and I'll zoom back out a second time, and this time I'll zoom into the next peak. And if you notice, there's a little bit of junk around this peak too, and that's okay. It's a real device, and with real device, there's complexity, and with complexity, you'll get a little bit of junk. All right, so I'm going to zoom in like that, and I'm going to do the same thing. Analysis fitting. Actually, I'm just going to go nonlinear. Sorry, this one is the nonlinear curve fit last used. I could do that. And I'm going to look at what the peak looks like, and it's a pretty good fit again, and so I'm going to go ahead and hit fit, and go ahead and hit no. And I could go and find the standard deviation of residuals. You should probably do that. But I'm not going to do that. You know what? I'll just show you where it's at. All right, so there's my two frequencies, 115.9 and 348.2. Does that sound like a harmonic to you or not? All right, so let's go to our peak fit data. So to do that, I'm going to click back on the data sheet, and notice how I have a couple fits down here. We got, first of all, the graphical results of the FFT. Now we have our first curve fit, and this is the parameters that it fit, the little report sheet. Now this is the important sheet right here. See this regular residual of B magnitude? I could have actually turned off all the rest of the residuals, but this is the only one I really need. And so I'd go right click. Oops, sorry, I wouldn't right click. I'd hit the statistics button. And with the statistics button, I can do quantities, and I could uncheck all of them except for the standard deviation. That's the only one I really I'm really worried about. So I could just check those, and now mine's just off the screen, so because there's a lot of quantities we can check it. We can click OK, and this time we could go to the report sheet, and it says my standard deviation is really, really big for the magnitude. But remember, the overall magnitude was really high, and the standard error was calculated using the standard deviation. When you don't assign a standard deviation in origin, it automatically calculates it using it finds the standard deviation first and then calculates the standard errors using standard deviation. All right, so with that, that's how you're going to do some peak fits for some organ pipes. And that's it. Thanks for watching.